This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Morning, everyone. Hello. Hi. May I have your attention, please? All right, thank you. Yesterday we saw an example. It was about the three truss elements. They were fixed at two ends, and we applied an external force, which was 3,000 pounds at node number 2. So after finding the displacement at node number 2 and 3, and also calculating the reaction force, the last part of the question was about calculating the displacement at point x equals to 40 inch. As some of you noticed, and thank you so much for pointing out that point. It was really thrilling for me that I know that you're listening to the lectures and following the lecture. It's really good. I appreciate it. So there was a mistake here. So in the formula, U equals to U3 minus U2 over L times X plus U2. This is a displacement function within element 2. This is the formula that we derive by using the local coordinates for each individual truss element, which means that L in this equation should be the length of each individual element, which is 30 here, and X is the relative X coordinate of every point onto the truss element as compared to the the first node on the truss element, which is node number 2 here. Which means that at 40 inch, you need to subtract 30 inch, which is the first element, and then put 10 inch into the equation. And just in case that you are doubtful about that, is it right or not, the thing is, if you remember, if you put x equals to node number 2, it should give us the displacement as node number 2. And if you put the coordinates of node number 3, it should give you U3. So to just make sure that you are doing properly. This was the point that from yesterday's lecture. In the end, I went through the incline bar element formulation quickly. I'm going to recap it very briefly today. So again, when we have a bar element in the local coordinates, so we don't have any problem with all the element stiffness metrics and global stiffness metrics that we draw. So all good. But when we want to use it in the global coordinates, then we need to transform the element K-matrix into the global K-matrix. So for example here in this figure, x prime and y prime are the local coordinates, x and y are the global coordinates. So in the local coordinates, we only have 2 degrees of freedom, u prime 1 and u prime 2. But in the global coordinates, when we decompose the u prime 1 and u prime 2, you can see that we have some components in U1 and V1 and U2 and V2. So that's why we're going to have 4 degrees of freedom in terms of the global coordinates. And then we came up with the transformation matrix, which map the local coordinates into the global coordinates, U prime 1 and U prime 2 in terms of U1, V1, and U2 and V2. And then we did the same for the force nodal matrix and just got the same transformation matrix. And then when we went back to the formulation to find the global K matrix, the K matrix in global coordinates, we just figure out that to find the inverse of the transformation matrix, we need to make it square first. So that's why we added 2 components, V prime 1 and V prime 2, into the equations, although they don't exist in terms of the degrees of freedom for the truss element. So we know that they are 0. What we put them into the equations to make the transformation matrix square. And after that, by doing the inverting the transformation matrix, finally we got to this local stiffness matrix, like element stiffness matrix in the global coordinates. So C stands for cosine of the theta. Theta is the angle between the truss element and the x-axis in the global coordinate, and S stands for sinus. So the important thing here is, if I go back to the figure, right here. So how do you know that you need to use this theta, or you need to just put the angle that the truss element is making with the x-axis at node number 2? So is it theta, or is it like 360 degrees minus theta? So for example, theta is 30 degrees, right? And this is node number 1, and this is node number 2. So if you put the start point, if you put the start node at node number 1, then you need to put the theta equals to 30 degrees in all the equations. But if you want to put the start point at node number 2, then the theta would be 270 degrees, right? So it depends on what is your start point. So just be careful. And in the case that you put the point node number 2 for the start point, in the K matrix, it would be K22, K21, K12, and K11, right? The order of the nodes would be reversed. So just be careful about it. And this is a homework, which we have 3 truss elements. Each of them has their own angle. So then we need to use the global coordinates to derive the element stiffness matrix, and then put them together to assemble the global K matrix. So, I mean, in the weekend, on Monday, if you have time, just spend some time to solve it yourself and practice it. We're gonna solve it next week together. All right, this was a brief recap about the lecture 4. And in today's lecture, so all we learned so far was for 1D elements, right? Spring element, truss element. So today we want to know that what if we go for 2D space? So we're having like a triangular 2D element. then what would be the displacement function and how we can get to the element stiffness matrix. And in the second half of the lecture, we talk about the importance of the convergence. So imagine that we have a thin plate which is subjected to the tensile forces at to the two ends of the plate, which is telling us that this situation is plane stress. So we can go for the 2D plane stress elements. And if we want to use the triangular elements, this could be an example of the discretization, which is shown in the figure on the right. So the question here is, when do we need to use the triangular element? Why not using the quadrilateral element? So whenever we have irregular shape in the part or in the body of the structure that we want to analyze, it might be difficult to use the quadrilateral, like the regular quadrilateral elements. In these cases, we can go for the triangular one. And the second reason that might encourage us to use the triangular 2D element is the equations is much more simple as compared to the quadrilateral element. So it depends on the situation. If the problem is not that complex and the shape is not irregular, we can go for triangular elements. So if you look at the figure, like just look at the shaded triangular element, as you notice, each triangular element has two common nodes with their neighbors, right? So in 1D elements, like in the truss elements, we mostly have one common point between the two elements, but here we have more than one. So we have two nodes in common. So this is a point that you need to keep in mind when you want to do the assembly for the global K matrix, and which make it like a little bit more complicated. So now we want to calculate the displacement function for this individual shaded triangular element. So this is the general node numbers for a triangular element. So instead of using 1, 2, 3 for the node numbers, we used I, J, M here. Since we are in the 2D space, each node has 2 degrees of freedom. So in total, we have 6 degrees of freedom, which means that the element K matrix should be 6 by 6. So now, besides having Ui, Uj, Um, which are the x displacement for each node, we also have y displacement for these three nodes, Vi, Vj, Vm. And this is the way that we're showing the nodal displacement matrix. So after choosing the element type, the next step is driving the displacement function. Since we have three nodes, and in each direction, like x direction and y direction, we have 3 degrees of freedom, which means that for driving a linear displacement function for each of these two displacements, like u, xy, and v, xy, we need 3 unknown coefficients, which needs to be known. So if you remember about the truss element, in that case, we only have two nodes, and each node has 1 degree of freedom. Then we only had 2 unknown coefficients, A1 and A2, for the truss element and the K and the spring element. But here, for the 2D triangular one, we have in total for u and v, we have 6 unknown coefficients. So basically, uxy and vxy tell us the displacement at any interior point in the triangular element. And since we're using the linear function, it ensures the compatibility between the neighbor elements. So this is all right. We don't need to worry about it. And then if we want to just put all these displacement in x and y direction together, this would be how we can express them in matrix form by using the SAR. So we have a 2 by 6 matrix times by the nodal by the unknown coefficients, which is a 6 by 1 matrix. So now what we want to do is calculating the A1, A2, A3, A4, A5, and A6. Can anyone tell me how we can find them? It's exactly the same as what we did for the spring element and the truss element. Exactly. So do you know how many boundary conditions we do have? Yeah, I heard it, 6. So we do have 6 equations, 6 unknowns. To solving all the equations, we need 6 boundary conditions, right? So at any point, at any node of the triangular element, we know the nodal displacement. For example, at xi and yi, which is the coordinates of the node I, we know that the displacement in x direction is ui, and the displacement in the y direction is vi. And the same for the rest of the nodes. So if you write down these 6 equations together and then try to write down in matrix form, these would be the equations. And then for solving the unknown coefficients, we need to calculate the inverse of that matrix, which is the matrix X. So if you forgot about how to inversing a 3 by 3 matrix, you can just find it on the internet, please. Just update yourself if you forgot it. If you do the inversing here, you will get to these equations. So A is the area of the triangular element. And for making the equations more simple, we define some parameters called alpha I, alpha j, and beta and y. You can find these 6 parameters at the bottom of this slide. And then by using the alpha, beta, and gamma, we can find the unknown equations. This is for the unknown equations for uxy, and this is for the unknown coefficients of the displacement in y direction, or vxj, vxy, sorry. And now, if we expand all the equations together, and we want to merge them together and find the psi function, which was the general displacement, I'm going to go through them quickly. This would be the final psi displacement. So we have, again, 2 by 6 matrix times by 6 by 1 matrix. The first matrix is called shape functions. You remember N1 and N2 for the 1D element. Here, Ni, Nj, and Nm are the shape functions. And the second matrix is the nodal displacement matrix. Ui, Vi, Uj, Vj, Un, and Vn. So this is in the general form. So I haven't used 1, 2, 3 here to make it like general for all the types of the, doesn't matter like what nodes we're using for each element. And here is the how we can calculate the shape functions. There is an interesting point about the shape functions here. There are too many slides. I cannot put them together, but if you try to calculate the shape functions at each node, like node number I, which is xi and yi, if you try to calculate ni, nj, and nm at the coordinates of the node I, you will realize that ni would be 1 at that node number, and the rest of the shape functions would be 0. So what does this tell us here? It basically emphasizes that the shape functions at the corresponding node number should be 1, and the rest of the shape functions should be 0. So for example, if we look at if we put the coordinates of the node j, which is xj, yj into the equations, nj would be 1, and ni and nm would be 0. Doesn't matter what's the order of the shape functions. Here, all the equations are for linear functions, but if you even draw the quadratic ones, this is the rule. The shape functions at the corresponding node number should be 1, and the others should be 0. Any questions about the displacement function or the 2D triangular element? The reason that I put all these mathematical calculations here is I don't want to test you guys on this for the exam. This is just to give you an insight that what will happen if we go for the 2D space and then after that for the 3D space. What would be the difference between the 1D and 2D? I know it's pretty difficult to just write down all these equations by hand, and especially if you want to like solve an equation or problem by using the 2D space elements, it takes ages, and the size of the K matrix would be sometimes infinite, so it's so difficult to write it by using hand. So you definitely need to coding up in MATLAB or using the commercial finite element like Abacus, ANSYS, or CONSOL. But all I want you guys to learn in these 3 weeks is to getting some knowledge and fundamental concepts about the finite elements, and to know that what's going on behind the scene in Abacus or in CONSOL. So after deriving the shape functions and displacement function for the 2D element, the next step is just finding out the relationship between the strain stress and displacement strain, and then finding out the element K matrix. I haven't done it in this lecture, but just remember, just be careful that in 2D space, we're gonna have 2 strain instead of the 1 strain. It would be epsilon x, epsilon y, and also we're having 2 components of stress, sigma xx, sigma xy, basically 3. Sigma xy, the shear stress, and then we're gonna have heaps of the equation, and makes it so difficult to just find out the K matrix. So we're gonna leave the 2D space here, and then going for some tips and hints about the mesh convergence. So as you remember from the first lecture, whenever we use the numerical solutions or techniques, we basically introduce an error to the solution as compared to the exact solution or analytical solution. So sometimes we do have both solutions, and we can compare them and see that if the error is sufficient, if the error is small enough, then we can say that the numerical solution is valid, right? But the thing is, the reason that we're using the tools like numerical method is we don't have access to the exact solution. We don't know the analytical solutions. That's why we're choosing to use the numerical techniques like the finite element analysis. So now imagine that there's a complex problem. We don't have the exact solution. We solve it by using either your own code or using the commercial software like Abacus. How do you know that the solution is valid? We presume that you use the proper element type, you're using the proper boundary conditions and loading, so everything is fine. You're choosing the proper material. But in the end, how do you know that this error is small enough to neglect it? Any thoughts? Experiment would be a good one, but imagine that we don't have any experiment, we don't have any exact solution, but we validated our numerical model for some previous experiments, but not exactly for this problem that we want to solve for. No one has done it. So the important thing here is mesh convergence can affect the numerical solution accuracy. So it means that sometimes when you make the mesh refined, when you make it fine, you're getting more accurate results. So to find out that you already passed the mesh convergence, you need to do the mesh a couple of times when you're solving a problem using FEA. So you start with the mesh size, like let's say 10 millimeter, and you got a result, right? Then in the next try, in the second try, make the mesh half, like use the mesh size 5 millimeter, and then look at the results. And do again for the mesh size, for example, 2 millimeter or 2.5 millimeter. If you don't see too much significant change or difference between these results, it means that you're getting, your solution has converged already. And no matter how fine mesh you're using for the model, you already got to the converged solution. So the important thing about the mesh convergence is finding out the most optimum element size. To finding the most optimum element size, you need to at least do 3 mesh size, 3 different mesh size. So this is a figure about the mesh convergence. Probably you're gonna ask in the workshop assessment. So you'll be given a problem, you need to model it, and in the end, we're gonna ask you that, have you done the mesh convergence? What was the optimal mesh element? So you solve the problem by using at least 3 different mesh size, and then look at the results. It could be like the displacement tip, it could be the deflection tip of the beam, or displacement at the tip of the beam, or stress, or anything else that you are curious to know about it. And then try to plot the results in terms of the level of the mesh refinement, the number of the elements, and the order of the elements. And if you see that after a specific mesh size, you're not going to get more accurate results, it means that you already got to the convergence zone. But how can we do the mesh refinement? Basically, there are two ways to do the mesh refinement. One way is, it's called edge refinement, which means that increasing the number of the elements, making the elements smaller and smaller. And the second way is P refinement, which is basically increasing the approximation order. I mean by approximation order, I mean increasing the shape function's order. Instead of using the linear displacement function, we go for the quadratic displacement function. So here, for example, you can see that if we go for P refinement, it means that we want to increase the number of the nodes between each element. For example, for regular quadrilateral element, which has normally 4 nodes, if we go for quadratic shape functions, then we will have 8 nodes instead of the 4 nodes. And by increasing the number of the elements, which is really clear, so we need to break down that specific region or the whole thing to the smaller pieces of the elements. Any questions so far? So, for example, in Abaqus, I think most of you guys have done the workshop 1. So in Abaqus, when you choose the element type, there's a section, it's called geometry order. Geometry order is exactly indicating the order of the shape function. So by default, it's on linear, but if you want to go for P refinement, which is increasing the order of the element, you can change the linear geometry order to the quadratic or second order. Right, so we learned about the 2 different techniques of mesh refinement, and now, when do we need it? When do we need to do the mesh refinement? So, do we need to do the mesh refinement in all over the body, or we can just do it like at some specific regions? If you do the mesh refinement for the whole body of the structure, you basically increase the computational cost, which is not really reasonable. So you need to be careful that at 2 zones, we really need to make sure that we're using small enough elements. The first zone is when we have a rapid change in geometry, when we have a curve, like a hole in middle of the plate, or I don't know, like a sharp points or the curvy edges. This is where we need to use the small elements. The second zone is when we are expecting higher stress concentrations at some section or region of the part, we need to choose small elements there as well. There is a principle called Saint-Venant's principle. This principle is saying that when we move away from the local stresses, the effect of the local stresses cannot be observed as we're moving away from the location of these stresses. Which means that, for example, just imagine the plate with the hole at the center. So when we're moving away from the hole, we know that the stresses is getting to the stable condition, right? We're not going to have a rapid change and fluctuation in terms of the stress and strain. Then we don't need to use a very small elements there. We only need to use small elements at vicinity of the hole. And then when we just figure out at what sections we need small meshes and at what section we need large meshes, we can just go for transient mesh between these two sections, from the small element size zone to the large element zone. Whenever we use the term mesh refinement or mesh convergence, whenever we use mesh convergence, we're basically talking about the high stress concentration areas. So whenever we have a curvy edge or irregular geometry, we need to make sure that we're using small enough elements to capture the boundary there. So for example, look at this plate. So this is a 1/4 of a plate with a hole at center. If we go for big elements, large elements, we can see that in the first figure on top, we basically cannot capture the boundary of the hole, right? It doesn't look like a hole to me. So we need to make sure that in irregular shape and geometry, we're using small enough elements to just capture the boundary. And please don't misconfuse it with the mesh convergence. So this is two different things. There are a couple of situations that they're always challenging when we use FEA. And we should know how to deal with them. The first thing is singularities in the part that we're doing the analysis. So sometimes there are some sharp corners, could be because of a crack or I don't know, just irregular geometry, that basically the radius at those corners are 0. So from the theoretical formula, we know that whenever the radius is 0, the stress would approach to infinite, right? So in theory, there is no solution for singularities. For example, look at this plate. This plate has an edge crack on the left edge. The thing is, if you try to do FEA for this crack by assuming the 0 radius at the tip of the crack, and then try to find out the mesh convergence by making the mesh fine and fine and fine to find the ultimate converged solution. But it's very surprising that you will never get to the converged solution at this point, because the more elements you're using at that corner, the more the stress continues to infinity. So it keeps going up as you do the mesh refinement. So mesh refinement cannot help us in this condition. So now the question is, what is the solution for singularities? The solution is, in these types of conditions, we can simply replace the 0 radius corner with the actual radius, and then try to refine that region around that corner with sufficient number of elements. So this is how we deal with singularities. The next situation which is pretty much challenging in FEA is shear locking problems. So whenever we have thin structures like beam and we are applying pure bending onto the beam, in some situations this would be the final deformed shape of the element. So the black line is showing the undeformed shape of the quadrilateral element, and the blue line is showing after the deformation. So you remember from the pure bending problems that we only have normal stresses and normal strain. We don't have shear stress or shear stress in pure bending, right? You remember that? So, but if you look at the deformed shape here, you can see that the angles are not right angle anymore. So this is something like a bug in FEA. If you're using linear elements, first order elements for pure bending problems. So again, I know some of you guys having workshop 1 today evening, but just pay attention to this thing. In Abaqus, in workshop 1, we solved a beam which was applying, it was a cantilever beam with the pressure on top of the beam, right? And when we chose the element type, we went for a linear element, and then we changed the feature to the incompatible modes. So this is telling us that linear elements are not good for pure bending. But in Abaqus, there is a feature called incompatible modes. Whenever we go for that feature, it basically avoids shear locking, although we are still using the linear element. So there are two possible solutions to solve this problem. The first is doing the mesh refinement along the thickness by using the multiple elements or edge refinement, or going for the second order mesh, which significantly reduce the locking, shear locking effect. And this is an analysis which is done on the cantilever beam. So we have pure bending in this problem. We're using the quadrilateral, we're using quadrilateral elements and triangular elements. So if you look at the plot, the horizontal axis is showing the number of the elements, and the vertical axis is showing the deflection at the beam tip. So we have 4 plots here. 2 for quadrilateral elements and 2 for the triangular elements. Q stands for quadrilateral and T stands for triangular. 1 stands for first order element, 2 stands for quadratic element. So as you have noticed here, when we've done the mesh convergence, for the quadratic elements, either triangular or quadrilateral one, we can see that the solution converged quickly. But when we're using the linear elements, we need to do the mesh refinement at least a couple of times to get to the converged solution. And the reason that it's because of the shear locking effect when we're using the linear elements for pure bending problem. So again, if you're using Abaqus, you can avoid using the quadratic element by choosing incompatible mode for linear elements. Any questions?
Can you explain this shear locking effect a bit more?
Oh yeah. Here? So whenever you're using a linear element and it's in thin structures like beam, that we can basically go for 2D elements instead of the 3D elements, and we have pure theory, we shouldn't have any shear strain or shear stress, right? It's pure, so we only have normal stress, my over I equals to sigma, like xx, or in the direction of axis of the bending. But the interesting thing is, when we're using the FEA, it has been observed that the deformed shape of the element could be like the blue elements. And if you look at the angle of the edges of this element, they're not right angle anymore, although we use the right angle from the beginning. So the shear strain means the change between the angle of the two line segments in x direction and y direction, right? If we don't have shear strain, then the angle should remain unchanged. But here it changed. So this is an error when we're using the FEA for linear elements for pure bending. These are the things that if you have no idea about them, you never realize it. So to deal with this condition, we have two techniques to do. Do the mesh refinement or going for a higher order shape functions. Was it clear? It's pretty difficult to explain it, but there are heaps of the resources for shear liking and what is happening there. I mean, it's good to just
It's showing a shear effect, so it shouldn't be any shear effect.
exactly. We don't have any shear here,
Yeah.
but we can see shear in the deformed element, which is not true.
Would that happen if we did it by hand, or is it only on sling programs?
I think should be happening in both cases
Okay.
because that one is also using the same procedure.
Okay, shoot out linear approximation.
Yeah. Any other questions? Yes. Yes, singularity. Oh no, it doesn't mean to use that one. So you assume a reasonable actual radius at that corner, and then try to do the mesh convergence. Just figure out now when the solution converges.
Doesn't have to be.
No, it doesn't have to. I mean, it should be fine enough, but I'm not saying that too much, like small elements there. You need to do the mesh refinement, mesh convergence to double check that it's completely right. Any other questions? Yes.
With the plot on the next page, the convergence plot was 4 lines on it.
Yeah.
Why is there differences between the...
So the shear locking is originating from using the linear elements or pure bending, right? So there are two solutions to conquer that problem. One, increasing the number of elements, or going for the higher order of elements. Which going for higher order is more recommended. And this is showing why. So the two top are Q2 and T2, which are quadrilateral element and quadratic triangular element. So it's showing that we don't have big fluctuation if we go for small elements.
Also, Q2 is meant to be quadratic, quadrilateral.
Exactly. 2 stands for quadratic function. Oh yeah, sorry for that. Q2 is the quadratic. Yeah. It's a typo there. Alright, so I mean the FEL lectures are finished here. So from the next week, we're basically having the mid-semester test on next Friday, exactly the same time, same venue. And in next week on Tuesday and Thursday, I'm gonna go through like homework 1, homework 2, and solving more examples. So don't please feel stressed out about the test. It's gonna be completely the same as what we learned here, and pretty much similar to examples and homework. There would be 2 conceptual questions, like the ones that we learned here about the shear locking or about the mesh convergence, and one calculation problem, which could be very similar to homework 2, might be. All right, thank you so much. Have a good weekend. I'll see you next week.
For this chapter, do you use Logan's book?
Yes.
Which chapter? 11?
Just double check it. I mean, it's one for one the element, like
Yeah.
the spring element and thrust element.
Thrust
This two.
Okay, for this one,
This one, just stick to it. But if you want to know more about it, just search it on your own. I'm not gonna ask you something which is beyond these slides. Don't worry about the conceptual.
okay.
But if you want
Because
to know
if
more,
read Logan, it's
yeah, I mean the best thing is just Googling for these things because the books usually don't cover these things that much.
okay.
But it's good to just go to the forum and see that what people are talking about.
And I don't know, do you have prepare trial for mid-exam, like pass
Like
mid-exam?
the homework 1, homework 2, that's pretty much the same stuff.
Oh, okay. So, I don't know, how many questions for
2 conceptual and 1 calculation.
Thank you so much.
Hey.
Like, according to continuity and extra requirement if you want to go from quadratic, they can't just
Here,
yeah.
increasing number of the elements, right?
So wait, no, sorry, for P refinement.
Oh, P refinement.
That has to be over the entire void body, right? Because you can't have part of it linear and part of it quadratic.
You can,
Okay.
but I don't suggest it.
Okay.
I mean, just to stick to like the same order.
Yeah, because it seems like I don't really understand why when you would go for P refinement, if you could just increase the amount of nodes in the areas of importance, because that seems like the biggest.
Yeah, I know what you mean. So I feel that there are some situations like in the geometry, it makes it difficult to go for small elements like in that like I don't know like irregular shape. You know what I mean?
Okay.
Sometimes it's difficult, so it might be better to go for edge refinement. And the other application of edge refinement is the shear locking effect.
Yeah. Okay.
I mean, it would be much better to go for higher order of, P refinement, higher order of the shape functions instead of the increasing number of the elements.
Okay. Is there a big like, computational cost difference between opting for one over the other?
I think I cannot compare these two refinements together, but that's a good question. But also it's my question as well.
Okay.
Like,
Yeah.
at what point that they're gonna be pretty much the same computational
Yeah.
cost?
Yeah.
But no,
Because that sort of relates to my question about whether
yeah,
if you have to like increase the approximation over
Yeah.
the entire thing, then
I
that
think
seems
that
like a
one
big
is.
cost.
I think that one is faster still,
Okay.
using the higher number of the elements, but with the linear elements.
Yeah.
I think that is faster.
Okay.
But that's a good question. I'll look it up.
Yeah.
Hey.
So we're both. We're just a bit confused on the step process of how you go from like that point to that point. Like, what I'm understanding is that's like a chaos. So why is it versus we do the
Right. So this is the formula for the local coordinates, right? And now what we want to know is, what is this formula in the global coordinates, which is F, K, D, right? And the reason that we want to find this out is to calculate in this K matrix in global coordinates. So we know the relationship between D and D prime. We know the relationship between F and F prime, right? By using the transformation matrix. So we're gonna start from this. So instead of the F prime, I'm gonna put F and T, which is the transfer matrix and F, right?